Okay, so Amok submitted his answer for the fun problem. For those of you who are just joining in, let me just paste the fun problem because I think that chat is not, you don't see the previous messages in the chat. Okay, so fun problem. Yeah, so Amok gave the answer. Let me not tell the answer is correct. I can tell it to Amok privately. Yeah, otherwise you're welcome to make your answer. As always, in my fun problems, there's a catch. Okay, let's get started. So yesterday we talked about areas, lengths, and so areas under the graph parameterized by equations x of t and y of t. And we talked about lengths of arcs of those curves. And finally, in the end, we talked about the rotational curves, areas of surfaces which are obtained by rotation of the curve about the x-axis and about the y-axis. So these are standard calculus tools which become even more effective when we use parametric description of those curves. And so we have derived all the formulas. Everything was done from scratch, and I think we'd appreciate the beauty of the presentation. So the as always in calculus, the idea is that we start with something small, like here in the example with areas, right? First you compute the area of the surface of the small cone surface, right? And then if you stack these cones one on top of another, and in the limit when the length of the step of the cone becomes small, the sum converts into a Riemann integral. So, of course, we're assuming that all functions here are continuous, right? So if we have a continuous function on a segment, then on a closed segment, then you can always integrate it. Then the Riemann integral always exists, right? So there's a theorem like this in calculus of one variable. Are there any questions? Okay. So today we'll talk about polar coordinates first. Small here. So this is lecture 4. Okay, so and that covers in the book the 10.3 through. Well, we'll see how far we can get. But if you won't have time to talk about conic sections today, we'll talk about this also. We'll talk about this tomorrow during the discussion. So given the fact that we don't have quiz this week, we have a little bit more time for lectures. Okay, and what I want to talk about today is polar coordinates. So this is how it works. You take, let's start with the Cartesian coordinates. Right, so this xy plane, which we know and love, and a point in xy plane is given by a pair of two numbers, x and y. So x and y can be any real number, right? So x is length of this segment from the origin to this point, and then y is this point. Now, let's draw this straight line that connects the origin with point xy, and then in fact let's call point xy a, right? So it will have a shortened a. Let's evaluate the distance, right? Let's evaluate the distance between OA, and then we can call this R. So the distance between O and A, also let's call it R by definition. well, R should carry index A, but doesn't really matter here because there's only one point. And of course, we know that this is from Pythagorean theorem, this is the square root of x squared plus y squared. And so this is R, this is x, this is y, and we're in the straight straight triangle. So the idea of polar coordinates is to change the parameterization of points in the coordinate plane by switching to the absolute distance to each point from the origin r, and the angle which this line, which this ray OA makes with the real axis, excuse me, with the x-axis. So let's call this angle. Let's call this angle theta, right? So we know that for example, we can write any trigonometric function we like. For example, tangent theta is equal to y divided by x. So theta will be the inverse tangent of that, right? So the idea of the polar coordinates is to switch from the description of x and y to r and theta. Using this formula over here, let's write them again. So we want to have, so r is equal to, so we want to be able to change coordinates in both directions, right? So first we can say that r is equal to square root of x squared plus y squared, and tangent theta is equal to y over x, or the inverse, right? Maybe I can ask you, so what should be the formula that describe transition from x to r and theta and y to r and theta? What's the, what these formulae are? We can read them off from the right triangle over here. That's right, so Hannah is given the right answer, so it's r times cosine theta. It's kind of hard to read without spaces, but yeah, this is correct. R times cosine theta, and y is equal to r times sine theta. So if you haven't learned later yet, you would say something like this, so r times cosine theta like this, right? So cosine and theta both comments, defined comments in later. Yes, this is correct. Good. Yeah. So that's what polar coordinates are. Now, so we know that in Cartesian coordinates, Cartesian due to Descartes, right? So Cartesian, you know, in French, like the ds, it's like it's the you don't use it if you do the conjugation of the word. So that's why it's not des Cartesian, it's Cartesian. So these are Cartesian coordinates. And yeah, so and these are polar. Now sometimes this axis is called polar axis. And theta is the polar angle. We can just call it angle, doesn't really matter. So in Cartesian coordinates, every point is given a unique address, right? So there is, for every point on the plane, there is a single pair of numbers x and y, right? Such that that point is given by these coordinates. Do you think the same is true for polar coordinates, or maybe there are points which are a little bit exceptional? What do you think? Like, are all points equal, on equal footing in polar description, as opposed to the Cartesian? Every point has an infinite representations. Yep, very good. Yeah, that's right. So, good. So, Jonathan, you made a great point. Now, let's actually fix theta to go between in fact, yeah, we should start with that, between 0 and 2 pi. And you can see here, I do not include the boundary with 2 pi, right? So that all points on the polar axis, say this point, will be characterized only with angle 0, not only 2 pi. Okay, what else? So modulo this comment by Jonathan, which we fixed by restricting the range of theta. What else is going on? Yeah, so what Charlie is saying, the 2k pi, right? So we took care of this by specifying the boundaries. So you cannot go to k above 1. But okay, so maybe if the question might be not very clear, let's do the following exercise, right? So let's look at Cartesian planes. I'm gonna make it 2 parallel pictures here. See Cartesian and polar plane, right? And then let's talk about lines of constant. So in Cartesian coordinates, what are lines x equals constant? Say x equals c1, right? So these are lines of which are parallel. This is not parallel, so these are lines that are parallel to the x-axis, right? Well, r is positive by definition, right? So so here we see r square root of x squared plus y squared. We know that it's actually, yeah, it's non-negative, right? So it can be 0. If both x and y is 0, if you sit in the origin, then r is equal to 0. Okay, so since Alex talked about it, what happens when r is equal to 0? What happens with the angle? So when r is equal to 0, we sit over here at the origin. Yes, it's a point, but no angle. What? So one way to say it, there is no angle. Yet another way to say it is that angle is undefined, right? So that indeed, if you sit at the origin, like it doesn't matter where you rotate, right? So when you are at the North Pole of Earth, your latitude is not really defined, right? It will be defined immediately when you step out of the North Pole, and then you can do the round the world travel around that point. But at that point per se, it's not defined. So let's make a comment here. So it's a little artifact, sort of little bug of polar coordinates that they don't particularly well work with the origin, although for most of the calculus applications, it's no problem. So when r equals to 0, angle theta is undefined. But like I said, it's no problem. Okay. So yeah, so these are x and y. Let's just see what happens when so this is C1. Switch the color. C1, C2, C3. These are lines of constant value. X equals Ci. Now, if you say y is equal to, let's put another constant, di, those will be lines that are parallel to the x-axis. Right, so it would look like this. You have D1, for example, D2, D3. Now, so yeah, and in fact, yeah, we know this very well, right? So in fact, every point in the Cartesian plane, so this one, it will have coordinates C2, D1, right? So that's how you find coordinates of each plane. You would find a line that is parallel to the x-axis that passes through that point, and then you find the line that is parallel to the y-axis that passes through that point, and that fixes you immediately the coordinates. Now, in polar description, we have r and theta, right? So then the r equals constant, let's say r equals to r1, right? So what is the set of points, set of all points in the coordinate plane, so that the distance from the origin to the set of points is constant? How do you call this set? Circle of radius r1, absolutely, yes. So indeed, so this is one circle, this is another circle, this is another circle. So here I drew 3 circles with of increasing radii. Okay, so this may be R1, R2, and R3. Okay, so, and then indeed, so if you pick a point, and so every point on the circle of radius R1 is R1 units away from the origin, and it's true for every angle, right? Okay, and then how about, so you can have, and then how about theta? So theta is equal to theta 1. What is the set of points that is described by equation theta equals a constant? How does it look like? A line, yeah, that's right. A line with sloped tangent, Yes, yes, that's right. Indeed. So just by definition, so theta is just the angle that a ray starting from the origin and going to the point we're talking about makes, and then if we require that this angle will be the same for all points of that set, it simply means that it should be a line, right, which makes, well, now the plot is a bit over abused, so let me, where can I put it? Let me just make a separate plot. Oh, maybe it's okay, yeah, so this angle is theta. Theta 1, and then if you're gonna do several of them, say theta 1 big less than theta 2 less than theta 3, right? Then they would go like this. I just drew 3 random rays, right? So yeah. Yeah, good. So indeed, what happens as you do this transformation, right? So as you go from Cartesian coordinates to polar coordinates and apply these formulae, what happens is that this mesh, this grid of parallel vertical lines and parallel horizontal lines becomes this interesting sort of network of concentric circles around the origin and radial rays that go in all directions. One more comment here. So this choice of boundaries, right? This choice of boundaries here is really up to us. So we can always say that, okay, theta is positive and measure it counterclockwise. But for some reason, you may try to do it, to measure it, to go in opposite direction, right? But still, when as we discussed, it doesn't really matter because you can always reassign the angle as if it was an angle between 0 and 2 pi. So say we're here, right? This is where our point is. So according to our rule, this should be the angle theta, right? So therefore, and then of course, or equivalently, you can say, okay, I'm just going to go down and say that this is the so this angle. How want to call it? Yeah, I guess I want to call it say phi, right? And then of course, if phi is negative, right? So if phi is less than 0, you should replace it. Then phi is equal to 2 pi. So yeah, so phi should be negative, right? So it should be a theta minus 2 pi. Yeah, so of course, this choice will not change the assignment of coordinates, right? So if you calculate the position of this point, right, it would be r times cosine phi, r sine phi, right? And of course, because sine of phi is negative, so it doesn't matter if you substitute phi or theta minus 2 pi, it will give you the same answer. It will be described by the same point. So sometimes it's convenient to use negative angles, but we also know that you can always replace it with a positive angle, sort of that goes around the which is bigger than pi. Okay, so let's now, any questions? Now let's talk about parametric curves in polar coordinates. Let's try to once we introduce once we understand what they are. So essentially it's a different coordinate system, which is, well, you can see it's convenient to study shapes that have certain rotational symmetry or some part of this rotational symmetry. As we will see below, it will be more convenient to use polar coordinates. So when we'll talk about three-dimensional shapes, so three-dimensional curves, we'll see that there are even more, right? So there are so-called spherical coordinates, when you would kind of tessellate your space in concentric spheres, and then you would locate the point of the sphere. Parametric curves in polar coordinates. Okay. So before, in Cartesian coordinates, we had what? We had a set of equations: x equals x of t, y equals y of t. And now, well, in principle, we can have what? We can have, most generally, we can have something like, in polar coordinates, r equals r of t, theta is equal to theta of t, where t will be an independent parameter. However, for a lot of applications, it's convenient to use theta itself as a parameter, right? It won't give you all the possible curves, but as we'll see later, it will cover a big subclass of them, right? So, but in particular, as a particular case, we can study curves which are parameterized by, say, r is a function of theta, right? So it should be understood like this, that you vary theta from 0 to 2 pi, and then r of theta is a certain function, explicit function of theta, which we will plot, right? So it's like it's the polar coordinates analog of just y equals f of x, right? But only now, because we live in this polar world where things look a bit different, I think it's a good idea to understand how this parameterization works. Okay, so the first example, which is trivial, r equals 5, right? We know what this is. It's a circle of radius 5. We just talked about it. So it's a constant function, constant curve, but because we live in polar coordinates, it's a circle. It's a circle of radius 5. Okay. Well, now let's do something less than trivial. Like, let me zoom. I reached the end of the page. So because after today's lecture, I'll get the I'll upload the updated version of this PDF. Yeah, this way, the entire first week will be on this big, well, on the big page, so you can review it. Okay, so the next example. Let's do something different. Let's say r is equal to 1 plus sine theta. Right, so it's something really which looks really simple, simplistic, and innocent. But let's just try to plot it. So remember here, so theta is a polar angle, right? It varies between 2 pi between 2 pi and 0. So what we need to do is just to carefully draw it on the plane with polar coordinates. Right, so we don't have to put x's anymore. We just know that. Well, yeah, then we can let's make a little table here, as we used to do. First, in fact, here, because there's no parameter, we can just do it for just theta and r. And yeah, so before we go, it's useful to recognize if the formula, if this function has some symmetries, right? So what kind of symmetries does the sine function have on its period, right? So when you draw a sine function, in fact, it might be even help to draw the whole thing. Well, you can try to draw this in Cartesian coordinates, right? So in Cartesian coordinates, by which I mean the following. So we just literally put theta here in x-axis instead of x, and r instead of theta, right? And then I'll probably need a little bit more space. Yeah, let me do it carefully. Oops, I killed too much. Yeah, so in Cartesian coordinates, we're down probably, right? So the since we lift it by 1 unit up, right? So then we can draw this line when r equals 1. And then there will be a sinusoid around that point, right? So it will touch 0 and then come back again. So when this is 2 pi, and this is pi, here we have 0 at 3 pi over 2, right? And then, yes, and then here we have 2 at pi half. Okay, so in fact that will help us to draw to make the table. So yeah, so when r equals, so theta equals 0, r equals 1, theta equals pi half, r equals 2, theta equals pi, r equals 1, 3 pi halves is 0, and then 2 pi r is equal to 1 again. Okay, let's draw it first, and then I'll talk about symmetries, right? So then, so when theta is equal to 0, r is equal to 1, right? So it's which means that we are on the polar axis. And so when theta is equal to pi half, we should look here. So in the pin in purple, I'm going to draw the values of theta. Where is it then go? It's pi half, and then and theta is equal to pi. So we should be here. The value is equal to 1. Oops, didn't do it symmetrically. Oh no, my neighbors start their thing again. Always when I give a talk, I mean, it's so annoying. Yeah, one second. Should probably put a sign or something, like work in progress. Okay. So this is theta is equal to pi. And then 3 pi over 2. And then we come back again to 0. Well, it was not vacuum. It's the blow, whatever, the blow gun for leaves. But now they're cutting trees. Okay, so we have 5 points, and the two of them are coincident. What it doesn't give us too much of leverage, right? It's just 4 points. We need a little bit more, right? So I think we can. What basically we see here that if we the value of r rises, right, at this part of the curve, it rises from 1 to 2, and it does so sort of in a so this curve is concave down, right? So its second derivative is negative. So therefore, we should expect that distance from the origin to points on this curve will go. So because of kind of this arching of the sine function, right? We expect that the curve will do something like this, like that, right? Because because the distance grows, and it does so in this way. So in other words, like the distance, these distances, they will grow faster than linear, say, right? So that's why we expect it should sort of concave out like that. And so we'll check it later on the computer, but basically you can see here. So if say evaluate it at pi over 4, right? Let's do this evaluation. So when theta is equal to pi over 4, so r of pi over 4 is equal to 1 plus 1 over 2, right? And well, it's somewhere here. Pi over 4. Okay, now we'll also expect some symmetry. So like you see here, if you cut this in half like that, then the left half of this sine bell would be sort of symmetrically reflected here. And then therefore we expect that the left half of this upper dome will also be symmetric relative to a change of theta to pi minus theta, right? So this is the symmetry that I was talking about, because sine pi minus theta is equal to sine theta, right? Because by definition, yeah, good. So minus is a bit different. So this we don't quite have that yet, right, Julian? So so sine is an odd function, but I'm talking about different symmetry. Yeah. What I'm talking about also will be applicable, but not in this example. Yeah, so everybody agree with that. It's just the definition of the sign follows from the definition of the sign. So therefore, there will be symmetry like that. It will look symmetric. Okay, and now we need to find out what happens between pi and 3 pi over 2. Well, so again, we should expect symmetry relative to the vertical axis because, well, let's look here, right? So this and that are symmetric. So let's see what happens when theta is equal to how much it should be 5 pi over 4, right? So 5 pi over 4 is a point which is halfway between pi and 3 pi over 2. It's pi plus 1/4 pi. And well, it's this point over here, right? So it's value that's where we are. So it's equal to 1 minus 1 over 2, which is a bit less than a half, right? So that's right. So root 2 is 1.4. So if you invert that, it will be a bit. Yeah, it's a bit bigger than a half, right? Okay, so it's like that, and then the other point will be symmetric, right? So this point here, and then we know that at 3 pi over 2 it should come to 0, so it should do something like this, like that, right? And then which then it should just symmetrically reflected reflected like that. Okay, so one thing that is not clear from this analysis is that what will be the behavior around the origin. Are we actually going to have a cusp like this, or it will be more smooth? And to understand that, we need to study tangent lines and do the calculation more carefully, which we'll do in a second. But are there any questions? So this curve is called the cardioid. Cardio, you know, it's a heart, right? So it does look like a heart if you are, if you have enough imagination. That does look like a heart. No. Okay, so now let's do let's see before we go to about discussing other shapes and symmetries. Let's calculate its study its analytical properties, right? So let's talk about tangent lines. Tangent lines in polar coordinates. So for us, it shouldn't be much new because we know how to study tangent lines for any parameterization. So remember, a tangent line is a line which is given by the equation y is equal to derivative of x at x0, x minus x0 plus y0, and the where f prime of x0 is the derivative. So x0 comma y0 is the point where we're studying where we're drawing the tangent, and f prime of x0 is the derivative of function f at that point. Now our function is given in this polar presentation, so we need to switch coordinates to describe it in that manner. So dy over dx by chain rule, right, gives us, it's the same as dy over d theta dx over d theta. And then if you bring back our formula, which I'm just going to write here for convenience, r of theta versus r is equal to x times cosine theta, y is equal to r times sine theta. So dy over d theta is r times cosine theta. Actually, yeah. So we have to be so, and now, yeah. So this is true. But in our parameterization here, r itself is a function of theta, right? So therefore, when we do this differentiation here, we actually have to use the product rule because the derivative of r is not trivial. So it's this plus different color dr over d theta sine theta, and divided by dx over d theta, which will be negative r sine theta plus dr over d theta cosine theta. Right, so and that's more or less it, right? So we cannot, in general, unless we know more specifically what is the formula, that's all we can get. And so that's what happens in general, and we just need to do this calculation for every particular instance that we're faced with. Why are they treating r like a variable and not like a constant? Well, so see, so when you have a curve in pole coordinates like this one, right? It's a set of points that is given by this equation, like r of theta equals 1 plus sine theta. So there's a functional dependence between r and theta, right? So and this functional dependence determines you the position of these points. So what we're trying to do is we're trying to find a point on that curve and find the tangent line to that curve. So the and the way to do it is to calculate the derivative dy over dx. But now, as you change y and x, right? So remember that when you draw the tangent line, we pick 2 points on the curve, we draw the line that connects them, and then we ascend 1 point to the other. Now, because these 2 points, they are located on this curve, which is given by the functional dependence between r and theta, as you change x and y, you also change r and theta, but in a very specific way, right? Such that r and theta are connected by this constraint. So that's why you need to take this into account. Yeah, that's right. So so this is the formula. It doesn't tell you much except that there is some rule that it's basically some recipe that you have to apply in each particular instance. And in fact, if I were you, I wouldn't try to memorize this formula because to derive it takes 1 second if you know how to differentiate. So it's much easier to just trying to memorize this thing per se. It doesn't make much sense to me. But we can at least we can see when to better understand what's going on with the tangent lines. Let's discuss when the tangents are vertical and when they're horizontal. Okay, so because, excuse me. Yeah. So this derivative here, so dy over dx is the tangent of what do I say? Yeah, so the oh yeah, and never mind. Yeah, that's right. So let's just do. Basically, we need to. So yeah, we know that tangents are horizontal. Yeah, we're just gonna say it again. So tangents are horizontal. Right. If dy over dx is equal to 0, which translates in our calculation to r cosine theta plus dr over d theta sine theta is equal to 0. And provided that the denominator does not vanish, right? Because remember we had this example in first lecture when numerator was 0, but also the denominator was 0. So this is equal to 0, and the denominator, because if it is equal to 0, we have to use L'Hopital rule, not equal to 0. So horizontal when the derivative vanishes, and then the vertical. If it approaches infinity, right? So if dy over dx is equal to infinity, and then here these two conditions they switch, right? So that you want the denominator to vanish, but you also need to require that the numerator is not 0. And if they're 0 at the same time, then you have to do the L'Hopital rule. So like technically this doesn't completely cover all the cases, but you need to sort of study it on case-by-case scenario. Okay, and now maybe I can go up a bit, and then we'll just do the formula or apply this calculation for the cardioid. So for the cardioid, I'm going to look at the bottom formula and reproduce it on top. So dy over dx is equal to r. So our r is, remember, is 1 plus sine theta times cosine theta plus, yes, if r is this, then the dr, the derivative r prime of theta is equal to cosine theta plus cosine theta sine theta divided by negative 1 plus sine theta times sine theta plus cosine theta squared. Okay, it doesn't give us any particularly beautiful formula, but nevertheless, how do you want to? So we want to factor it so it will be easier to find zeros, right? So let's take out the cosine theta out in the numerator, and then you'll get 1 plus 2 sine theta. And on the bottom, how should we do it? Well, it's the, if you want to factor it, right? So it's the 2 sine squared. I'm just going to do the simple computation. Okay, let's see here, because it's minus 1 minus sine squared theta, and then yeah, so plus cosine squared theta. And then, oh, I'm sorry, there's an error. Yeah, that's right. I see that, yeah. It's not, it's minus sine theta, yes. It's minus sine theta, minus sine theta, minus sine squared theta, plus cosine squared theta. And now I want to replace cosine squared with 1 minus sine squared. So this way, I'm just going to write on the bottom so I won't have to copy it all the time. So then I have minus minus sine theta. So 1 minus sine theta minus 2 sine theta squared. Okay, and this expression we can factor, right? So we can factor it like this. You're going to copy the numerator first. 1 plus 2 sine theta. And this guy we can factor as 1 plus sine theta multiplied by 1 minus 2 sine theta. Yeah, so you can check that if you open up parentheses here, you'll get this expression. Okay. So that's the value of the derivative. Now let's see where. Give us a little bit more space. We'll just keep the picture and then the answer. So let's find the place where it vanishes, right? So dy over dx is equal to 0 at which values of theta? Well, it's cosine theta is equal to 0 and 1 plus 2 sine theta is equal to 0. And then we can find this equation, solution for these equations, but then we need to check that the denominator does not vanish. All right, so at which values of theta dy over dx is equal to 0, right? So cosine vanishes what? At pi half, right? So this vanishes at what? Pi half, 3 pi over 2, right? And that's it, because it's between our theta varies only till 2 pi. And the second equation, we say that it's sine theta is equal to minus 1/2, right? So it's negative 30 degrees and negative 150 degrees, right? So in terms of pi's, it will be what? It will be 7 pi over 6, right? It's like the 210 degrees, right? And what's it? 11 pi over 6. Okay, so that's the numerator vanishes at these points. And then denominator, well, so it's sine theta is equal to negative 1, as well as sine theta is equal to 1/2. So sine theta is equal to negative 1 is when you have, what is it, the 3 pi over 2. Right, and then the sine equals 1/2 happens at 30 degrees and 150, right? So it's pi over 6 as well as 5 pi over 6. Okay, so what do we see? So see our we really need to be careful because 3 pi over 2 appears twice, right? So and at this at this value of the polar angle, we have something interesting going on because, well, we essentially have to use the L'Hopital rule, right? And it's not surprising because the point 3 pi over 2 is this interesting point at the origin, right? It's presumably there's a cusp, right? At least that was the case when we talked about a cycloid, so the different parametric curve. So let's talk about 3 pi over 2 in a second, but for now we can just plot what happens when what happens with the other zeros, right? So pi half, 7 pi over 6, 11 pi over 6, the tangent is horizontal, right? So indeed, this one, this point, and that point. And so here it happens when theta is equal to 7 pi 6, and this is 11 pi 6. Okay, now, and tangent is vertical when angle is pi6 and 5 pi over 6. Okay, there's no problem. So I think that would perfectly serve as well. So it's the do it with a zoom. There's one here, and then there's one there. So this is 5, 6. Let me erase pi over 4, we don't need it. Okay, this is 5 over 6, and this one is 5 over 6. And now we need to study carefully what happens when theta approaches 3 pi over 2. And then, in fact, let's do it two ways. We'll calculate the derivative from the left and calculate the derivative from the right. And that will sort of tell us for sure what's going on. What kind of, so clearly we know that it looks like a spike, right? But it can be spike like this, like a wedge with finite pairs of derivative, or it can actually be a spike where both derivatives blow up. So let's calculate limit as theta goes to 3 pi over 2. And then, yeah, we'll do it plus minus 0. We'll do it from both sides. Yes, of that formula. Okay, so we have a, I'm just looking at the formula above here. So 3 pi over 2 came in a cosine, right? So it's cosine theta over 1 plus sine theta times 1 plus 2 sine theta over 1 minus 2 sine theta. So the reason why I factorized it is because the second fraction behaves fine when theta is equal to pi over 2. It is the first one which is a problem. Right? So remember, if you have two functions, right, the limit of the product is product of the limits if both limits exist. So therefore, we can write it as we can just evaluate 1 plus 2 sine theta 1 minus 2 sine theta at theta is equal to 3 pi over 2, because we know that this is a continuous function at that point. However, the first fraction is not, right? So then we need to do the L'Hopital. So times limit theta approaches 3 pi halves plus and minus 0. And then we derive the numerator, it's minus sine theta. And the denominator is cosine theta. And indeed, we see that it blows up, right? So so cosine when so sine of 3 pi over 2 is a well-defined expression, is -1. Can we also just, well, I mean, we can just plug it, right? It's 0 divided by 0. It's an indeterminate expression. That's why we do so the reason why I factored out the first fraction is because it's well-defined, right? It's not, it's like a constant which you can take out. So the reason why I did this is because, I mean, otherwise we will have to differentiate the whole thing, and that will be too cumbersome. Like the derivative will accumulate, will give us many terms which we don't need. Okay, so indeed, so that gives us infinity. So as we approach, right? So sine theta is equal to, so sine of 3 pi over 2 is equal to -1, right? And there is extra minus. So the numerator approaches 1 as theta approaches 3 pi over 2. Doesn't matter from which direction. And the denominator approaches 0, right? So if it approaches 0 from the right, so if it approaches 0 from the right, we get plus infinity. If it approaches 0 from the left, we have minus infinity. Okay, so that's equal to 1. So I'm going to evaluate this coefficient first, right? So it's, so sine 3 pi over 2 is -1, so it's 1 minus 2. divided by 1 plus 2, okay, times this limit. Theta is equal to 3 pi over 2 plus minus 0, 1 divided by cosine theta. Now, this prefactor here is equal to negative 1/3. Okay, so therefore, this extra minus sign, it will change the order of things, right? So therefore, when let's try now to space. Therefore, the limit of when theta goes to 3 pi over 2 plus 0 of dy over dx, that will give us minus infinity, and limit as theta goes to 3 pi over 2 minus 0 from the left of dy over dx is equal to plus infinity. Right, so the infinity is switched because of this minus sign. And indeed, we can confirm it with our plot. When we approach theta from the left, the 3 pi over 2 on the left, the derivative goes to plus infinity. When approaches from the right, the derivative becomes minus infinity. Okay. Good. That's it. That's the full analysis with the derivatives. Okay, good. So let's make a quick break. So I think we suggest we continue at 11:15. And while we are doing the break, I'm going to flash again the problem about the fun problem for today about hungry worm. And yes, I'll be back in a couple of seconds, couple of minutes. Okay, so through how many pages of the book did the worm chew? We have one answer so far submitted. Right, so with the two, I think, so it does disregard the covers. So think of it as like you have a 1,600 pages, you just printed them and put them on the shelf. And then you do not count, let's say you start counting from the next page. It's like if it says from the first page of the first to the last page of the last, so these are the pages which are not eaten by the worm. So like the worm starts eating the next from the first one and the last before the last one. So Daniel, do you want to amend your answer then, or still think it's 802? Well, 1,600 is the most naive answer, but as I said, the problem has a catch. Yeah, so John, so okay, so there are all variety of answers here. So some of the answers are off by 2 from the round numbers. I think these factors of 2 may come from the fact that this is like I said, do not count the first page. Well, 799 even. Hmm. $96. So you use throughout for the cover. So forget about the covers. No covers. Like I'm not sure why the answer is not round. So to say it starts eating from the first page of the first, and that first page of the first book is not being eaten, right? The next one is and on, and then the worm stops right before the last page of the last one. So the key point is that they stand next to each other, right? So it's like it's a four volumes that stand on the shelf next to each other in order 1, 2, 3, 4. Okay, I can tell that so far there is one correct answer in all chat history. You can decide which one. I can continue with the lecture, and then in the end we can check again the answer. Okay, so right, so we did the. Okay, I'm gonna respond to some of you individually. Yeah, so if you got a response from me that the answer is correct, then otherwise it's not. This problem is taken from the math circle for elementary school students, so you don't need to know any calculus to answer that. Okay, so where we're going to go next, right? So then well, let's maybe do some plotting on the how to get from the first limit line to the second limit line. Good. Okay. You mean from here to here? From sorry. This transition, yeah. So see, this fraction here is finite, right? As you take as state approaches by half. So you can think of it as just a constant, right? So if you have there's a theorem in calculus, right? If you have two functions, and then there's a limit of the product is equal to product of limits. So and because this second fraction is continuous, the limit of the function is just the value of the function at that point. So we evaluate this, and this evaluates to -1/3. Yeah, and for the first fraction, you need to use L'Hopital rule. Okay, yeah, maybe you can do some plotting. Okay, so so on mathematical Wolfram alpha, there is an option of polar plot. So let's do polar plot. Let's take this function. Let's check that everything is correct. And theta from 0 to 2 pi. Yeah, this is our cardioid, and you can just for fun play around. You can change some parameters here. For example, you can add some numbers here, right? So, for example, I put some number, say 1.1. Say change it a little bit. So see here, then the cusp, instead of the cusp, we have this little self-intersection here. It's like a swallowtail picture. And you can see as we increase that, this the size of the swallowtail thing becomes bigger and bigger. Yeah, so of course, if you make it really large, then it would almost look like another circle, right? So you can think of maybe like, but if this coefficient is equal to 1, then there's a singularity in the curve. But otherwise, this looks like a smooth. Curve. Okay, and then well, here's that example. If you say have cosine of 2 theta, right? So, for example, if you just do so when you do polar plot, that actually means that we're drawing a graph of the function r of theta equals some function of theta. Right, so here I put it denoted as t, but let me switch theta so it will be easier to draw. So that's cosine of 2 theta. You know, that's cosine of 3 theta. See, there's a symmetry here. Right. Now, obviously, like we expect that symmetry because of the nature of the function. So here, if you change theta by 120 degrees, if you add 120 degrees, then the shape should be self-symmetric, right? So on. So these guys form a pentagon. Okay. Okay, and then so this brings us to the following statement about symmetries. Let me just draw it. Let's talk about them, because it will help us to solve the problem quicker. And so first we have, I think one of you, I think it was Daniel or maybe somebody else, who mentioned the symmetry. If there's a symmetry, first type of symmetry is theta to the minus theta. If this is the symmetry, right, then the plot should be symmetric relative to the polar axis, right? Because so you have a shape like this, and as we discussed earlier in the class, if this is theta, this is minus theta. So the fact that, so by this I mean that the r of minus theta is equal to r of theta, right? If this is the case, then the graph is symmetric relative to the polar axis, because it just tells you that the distance between the origin and the point at minus theta is equal to the distance between the origin and the point at theta. So this is a reflection symmetry. under the polar axis. Okay, second, there's a, it's the symmetry that we had in the cardioid. So if there's a theta goes to pi minus theta, if this is a symmetry, so in other words, r of pi minus theta is equal to r of theta, again, as it was the case in cardioid, then there's a symmetry relative to the y-axis. We don't actually use y-axis in polar coordinates, but it's kind of, it's a kind of vertical. You can draw something that looks like cardioid. And so this is theta, and this is pi minus theta. So that gives us reflection symmetry. Under the vertical axis. Okay, what else? And then there might be a center symmetry. And one of the examples of the center symmetry we saw at I just showed you in Mathematica, right? So if you have this shape with two figure eights like this, so this is the center symmetry of order of degree 4, right? So it means that you can multiply. So if you replace theta with omega k theta, I'm saying that maybe in a little bit more formal way, but it's not so hard to understand. So where omega k is so-called the kth root of unity. Well, I just realized that would require complex numbers, but anyhow, so let's just say that here, if you can rotate it by some fraction of the full turn, right? So here you can rotate it by pi over 2, right? So basically, if forget about this, right? So it's the that requires knowledge of complex numbers, which we don't need to. If this is a symmetry, if this is plus 2 pi over k for some integer k, if this is a symmetry, right? So in other words, r of theta plus 2 pi over k is equal to r of theta, then it's called the center symmetry. So it's the center symmetry of order k. So here, this is the center symmetry of order 4. And then I showed you with order 5 and so on. In particular, if it's a symmetry of order 2, right, that changes theta to minus theta. In particular, theta goes to 2 pi minus theta, aka it's the same as theta goes to minus theta, is also an example of a center symmetry. And in this case, we should have something like this, right? Like the right, so yeah, this is 2 pi minus theta. That's right. Yeah. And then what? Okay, any questions? Good. Yeah, so this is an example of center symmetry. Right. Now, well, how much? We have like half an hour left. So so I suggest we do some exercises So tomorrow we'll have a discussion, right? So as I announced on B courses, there will be discussion for each section. So if you're welcome to come at 10 or you're welcome to come at 12, you can come at any time. And I think we'll start this discussion with a Q&A session. So I'll let you ask your questions, and after you're done, we'll solve some problems. And I was thinking to doing the area under the polar curves, under the area in the polar coordinates as a practice exercise for tomorrow. We can do that, and also calculation of arc length, right? It's a very similar calculation as before. All right. And then for the rest of today's lecture, I want to talk about conic sections and curves. So it's ellipses, hyperbole, parabola. So the idea behind, so we won't be able to derive the full story now because we haven't talked about three-dimensional shapes yet. So what is a cone, right? So you should think about it like this. It's a kind of, it looks like a sandwich kind of double cone thing with which is infinite, right? It's a three-dimensional surface. I show it sort of I show it a finite slice of it, but you should actually think that it stretches all the way to infinity. And now we can slice this shape with planes at various angles. Now, let's see what we can do here, right? So, and we're absolutely free to pick a plane in any way possible. So one way to do it is to take a plane and slice it horizontally, and then in the cross section there will be a circle. And so that gives us a circle. Let's just spell it out without too much of explanation. Sort of let's base our decisions on intuition, and later we'll be able to prove most of what I said. So that's that. Now, if you tilt this plane a little bit, and let me cut the upper side now. If you tilt this plane like that, and see what arises in the cross section, that will be an ellipse. So of course, circle is a particular example of an ellipse when its major axes are the same. Right? We'll talk about this in a second. And now you can imagine increasing that angle, sort of turning this plane up until you do, well, I guess I need a new cone here. Until the plane becomes parallel to the surface of the cone. So you kind of cut it like that. Didn't draw it well. So the plane goes like that, and it intersects the cross section. Look, it's a curve that looks like this, right? And then goes to infinity. And it doesn't intersect the second half wall because these two are parallel. Parallel to each other. Okay, do you know what this is? What's the name for the curve that we get here? What's the orange curve? Hyperbola. Okay, so are they parabola? That's right. So turns out that it looks a little bit different than hyperbola. Yeah, so this is the parabola. And as we'll see, hyperbola has two components, right? So to get to hyperbola, you need to keep tilting the angle. You need to keep tilting it upwards. In fact, I think we can do it here. So maybe I need a new cone. And then if you sort of, we can now make a, how do you want to do it? Yeah, so then you do, plane like that, right? So it would cut through both lobes of the cone, right? And then there will be one component here and one component there, right? So that is called hyperbola. Okay. Now, so yes, these are most these four kind of shapes are the most commonly discussed in this context. But out of curiosity, did we miss anything? Is there anything else which is sort of significantly different from hyperbola, parabola, point? Alex, how can I make the? That's right. So you can easily make the point if you take a plane and then cut it through the middle. There's a point. Very good. What else? Line. One line. How are we going to do a line? So yes, if you can explain it. Parabola, but on the cone. Oh, it's all on the cone. It's like it's hollow. There's nothing inside. It's like it's a two-dimensional surface. So you just cut it, and then it's always on the cone. I guess you meant something different. Parabola. But yeah, let's try to explore the option with line. Maybe you can have not one line, but more. Line up a plane with the edge of the cone. Oh, yeah, that's right. Good, thank you. Right, indeed, so we can pick a line like this. And then we'll go on the other side, right? And then like the plane would kind of, it will be tangent, in fact, right? It will be a tangent plane to, I guess the way you can describe it, it will be a tangent plane to the tip of the cone. And it will be tangent, it will have one ray on this side and then one ray on that side. Yes, very good. So we can have one line. What else can we do? Intersecting lines. Yeah, that's right. So and then once we know this, it's easy to make. You can just take again, it should be a plane, so sort of same plane if you tilt it up a little bit, right? So then we'll have a pair of lines. We have two lines like this. Line or two intersecting lines. Yeah, that's right. Yeah, so I think that's it. So it's a point, line, two lines, hyperbola, parabola, circle, ellipse. Yeah. So yeah, like I said, when we do the three-dimensional thing, we'll describe the cone as a three-dimensional shape, and then we'll give the equation for the plane, and then we'll solve the system of equations, so it will spit us out all the possible cases. Okay, let's talk about some of those shapes in detail, and then we're not going to talk about all of them. They're described in the book, and some of this will be left with exercises. Let's start with maybe with ellipse. Yeah, like that. So let's draw it in the Cartesian coordinates. So this is x, y, 0. So there are two distinguished points on the ellipse, which are called foci. So there are one focus and second focus. It's called F1 and F2. So F1 and F2 are foci. And you can think of ellipse as the following curve that if you take a point, say point P on the ellipse, and you calculate the sum of the distances, right? So we can define ellipse, right? So an ellipse is a set of points on the plane, such that the sum of distances from each point of the set to points F1 and F2 is constant, right? And you probably know that you can draw an ellipse at home as a part of small arts and crafts project. You just take a thread and then fix it at 2 points on the plane, on the cardboard, and then you just take a pencil and sort of draw an ellipse so that the thread is always at tension, right? So this way, the total length of the thread is fixed, and then that's why we'll be able to complete the ellipse. So here indeed, so as you can see, so ellipse is given. It depends on the choice of 3 parameters, right? So that's why it's called an ellipse. So it would depend on the choice of 2 foci, like where they are in the coordinate plane, and this distance, right? So which we call, let's say, F1p, right, plus F2p is equal to constant, and then let me call this constant to be equal to how do I do it? It's I think it's 2a, right? Yeah, that's right. So it's 2a, where a is the following thing. So a is the coordinate of the intersection of the sort of long part of the well, ellipse is squished in general, right? Since we call a the largest semi-axis. So this is a, this is minus a, this is called b minus b, and the distance from the origin to the focus is called c. Right. So it's the choice of F1 and 2 and a. And so these 3 parameters, rather, or in fact, if you only worried about like you don't worry where ellipse is in the coordinate plane, you can always shift it to the center. What actually matters is the distance, right? It's F1, F2, and a, which in our notation corresponds to the choice of a and c. So these are the equivalent sets of data. Or you can introduce the parameter epsilon, which is called eccentricity, right? It's a ratio of 2 parameters. And what I'm looking at is how to spell it. I'm I'm not good at spelling, so it's called the yeah. I think I spelled it correctly. So it's S. Oops. Oh, thank you. Yes, that's right. Eccentricity. So in other words, you can fix A like the semi-axis and the eccentricity. So that fixes you the ellipse, the ellipse in a unique way. Okay. So some identities on this data. So from the ellipse, you can draw it like that, right? So then because this is C, this is B, and the sum of the distances, let's call this point C, right? Because F1C plus F2C is equal to 2A, right? By definition, and then these are the same, right? So F1C and F2C are the same segment, so that for F1C, yes, F1C is equal to A, and from the right triangle, we get that A squared is equal to B squared plus C squared. Yeah. So another formula for eccentricity is that epsilon is equal to square root of 1 minus B squared over A squared. You can get it from here, and the okay now yes. We can now write the equation for the ellipse, right? If we take the, we already did it on the first lecture. So parametric equation will be x equals a times cosine theta, and y is equal to b times sine theta. Theta changes between 2 pi and 0, right? And then it's easy to write the equation for the ellipse. So if you have x squared, if you calculate x squared plus y squared, you're not going to get anything nice, but if you divide x squared over a squared and y squared by b squared, you'll get 1. So that's the that's the equation that gives an ellipse. And using our understanding of parametric curves, we can find the tangent lines, we can find their angles, etc. So I think we can either skip that or we can do it during the discussion. So I think later when we talk about vector calculus, I think I'll prove for you that there's three Kepler laws, right, which are so the reason why these shapes are so famous is because they describe how objects move in the field of gravity, right? So in nature, in gravity, the force, so that's a little bit of physics here, the force is inversely proportional to the square of the distance between two objects, right? So for example, sun attracts the Earth, the force at which it attracts Earth is inversely proportional to the distance, and same is true anywhere in the universe because laws of physics are universal. And from this fact alone, it is possible to derive, so by knowing what the force is and the laws of motion, from this fact alone, you can derive that that planets move. So assuming that the planet is assuming that it's not moving too fast, so planets, well, let's say travel travel along ellipses, right? So in other words, by using the simple laws of physics, we'll be able to, and a little bit of vector calculus, so we'll need a little bit of, we'll need cross product, we need dot product, and some identities on those vector quantities. I think it will happen in week 6 or week 7 of the course. We will derive this equation over here. Either this equation, or there's an alternative equation for an ellipse, which looks like, I'm gonna write it slightly differently. It's here. It's the radius r as a function of theta is equal to I think it's r, right? Yes, it's a divided by, well, it's some constant, right? So it's a divided by 1 plus epsilon times cosine theta. Only here, actually, I need to change the angle a bit, so it's not theta, it's, let's call it angle phi, because it assumes a slightly different parameterization of the ellipse, and so then the tablet froze, just 1 second. Yeah, you would put a center of the coordinates in one of the foci, because that's where the gravitational center is, and then angle phi will be the angle between polar axis and this coordinate and the planet, right? So, of course, for mechanical applications, it's useful to put the planet. It's useful to use this to this set of coordinates. Okay, and now in the remaining several minutes, let me mention the other curves. So planets travel along ellipses, but other objects that fly faster than the escape velocity, right? They can also travel along parabolae and along hyperbolae. And so also stellar objects parabolae and hyperbolae. And that depends on what is the energy of each object, right? So if energy is 0, then it's a parabola trajectory. If energy is positive, then it's a hyperbola trajectory. And if energy is negative, it's bounded, right? So it's an ellipse. So hyperbola looks like this, right? So you can have, again, so there are 2 foci. But now, instead of looking at sum of the distances, we will be looking at the difference of the distances. And it naturally will have two halves, 2 lobes, 2 components. So every point so naturally one distance will go is greater than another. So this is called C F2 F1. So if you look at CF1 minus CF2, and depending on which side of the hyperbola you are, this difference can be either positive or negative. So that's why we can take absolute value is equal to a constant, which is equal to 2a. Then, well, you can show that formally you can treat a hyperbola as an ellipse with eccentricity, with negative eccentricity. So if you kind of continue the eccentricity to negative values, you would formally, you'll get the same equations. In fact, the equation that I wrote above, it works for all three shapes. This one here, for hyperbola, for all the conic sections, in fact, depending on what you pick for the eccentricity. Okay. So this is hyperbola, and finally parabola. To define parabola, you just need only one focus, right? So you draw a horizontal line, and then you also calculating some of different distances from the focus. There's one focus here, F. To the set of points, and then you do the normal, the perpendicular line, and then you look at the, so let's say point big C lies in a parabola, and then you're looking for the set of points such that FC is equal to the distance from C to line, let's call it line L. Yeah, which is here. So just you can arbitrarily put a line. The way to draw it, you start off with a line, draw any line on the plane, pick a point F, which is a focus, right? Not on the line to get the parabola, and then you require that these two distances are the same, this and this. So this way you'll get the parabola. So in particular, see here, if you put this point here, right, so then the distances from the focus to the bottom to the minimum of the parabola should be equal to the distance from this bottom to the parabola itself. Yeah, and yes, we can call it. Never mind. So yeah, the minimum of the distance is called C. Okay. Okay, good. So that's it for today. Well, yes, like I said, tomorrow we'll start with Q&A. It will be like, an office hour, and yeah, we'll solve some we'll look at your homework. We'll solve some other problems, and I can answer your any other questions that you had. Is 2π included in the domain for the ellipse? No. Yeah, okay. I was just sloppy. Yes, you can remove 2π. Okay, yeah, I think, and finally, can somebody explain us the solution for the fun problem? So how about, who got the right answer? Vinay, would you like to explain? I think he left, yes. So the correct answer is 800 pages. And the reason for it is the following. So let me share it to you, share the screen. So see here, if you stack 4 volumes together, right, then the first page of the first volume will be here, and then the last page of the last volume will be there. So it will go like this, right? It will chew only through volume 2 and volume 3, which makes only 800 pages. Yeah. Is 2π included in the domain for is 800 because 400 multiplied by 2, not divided, right? That's right. So it's indeed. So it's actually, yeah. You have the important part was that you stack them 1, 2, 3, 4, one after the other. Okay, that's it for today, guys. See you tomorrow. Yeah, bye.